Welcome to question number 17 of our series on trigonometry worked out examples. Today the whiteboard is empty. I have not written down the question. That is because before we go to question number 17, I thought it's better to explain what is rational root theorem. Yes, there is a short detour to algebra today, but before we go to question number 17, I thought it's better to explain what is rational root theorem. It will be a very quick explanation. I'm not going to prove it. That's not the scope of this video. For the detailed proof, we will do a detailed video on algebra later. But for now, I'll just do the statement of the theorem and do two examples on rational root theorem. Okay? First, let us see what is rational root theorem. Suppose there is a polynomial p of n, where n is the degree of the polynomial, and the polynomial is of the form if we have a polynomial Pn which is of the form an x bar n plus an minus 1 x bar n minus 1 plus an minus 2 x bar n minus 2 plus and so on plus a1x plus a0. And if we have a polynomial like this where ai, that is an minus 1, an minus 2, etc., a1 and a0 are the coefficients of the polynomial, and if an minus 1, an minus 2 and so on, a1 and a0 are all integers, and a0 and an are not equal to 0, then all possible rational roots of this polynomial are of the form p divided by q, where p is the list of all possible integer factors of a0, the constant term, and q is the list of all possible integer factors of an, the coefficient of the highest exponent. And p and q will have to satisfy another condition. P and q have to be relatively prime. That is, when you are drawing the list of p divided by q, you will have to reduce p by q to its lowest term. May sound a little confusing now. Let me do a couple of examples. You will be able to understand very easily. Okay, first, let me write down what I have said till now clearly, then we will go to the examples. Okay, so this is the statement of the rational root theorem. What does it say? It says that if we have a polynomial like this and ai, which is an minus 1, an minus 2 up to a1 are coefficients of the polynomial Pn, and a0 is the constant term, and ai is set of all integers. That is, all these coefficients have to be integers. That is, it can be 0, it can be 1, 2, 3, 4, or minus 1, minus 2, minus 3, 4, etc. But an and a0 are not equal to 0. That is, an, the coefficient of the highest exponent, and a0 cannot be 0. That is, an comma a0 is not equal to 0. Then all possible, I have underlined possible. That means this theorem is not about finding the roots of the polynomial. This theorem only says all possible rational roots have to satisfy this condition, and if this condition is not satisfied, the roots are not rational. That's what it says. All possible rational roots of Pn are of the form p divided by q, where p is all integer factors of a0 and q is all integer factors of an, and p and q are relatively prime. Okay, as I said before, we will do two examples. You'll be able to understand very easily. Okay, let's look at our first example. Evaluate if p of x equals 2x to the power of 3 minus 13x squared plus 7x minus 8 has roots that are rational numbers, and we are going to apply the rational root theorem. Okay, here a0 is minus 8 and an is 2, because the constant term a0 is minus 8 here, and an, that is the coefficient of the highest exponent, that is x cube, is 2. So p by q is, integer factors of minus 8, which is our a0, and integer factors of 2, which is an. Let's write down. Okay, so what are the factors of 8? 1, 2, 4 and 8. And factors of 2, 1 and 2. Next, we have to write down all possible combinations of this ratio. That is, you have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8 in the numerator. And in the denominator, I have plus or minus 1 and plus or minus 2. I'll write down all the possible combinations. And these combinations are all possible rational roots of p of x as per the rational root theorem, right? Okay, so these are all the possible combinations of the ratio p divided by q. Let's look at these numbers. I'm going to explain what is meant by reducing p by q to its lowest term. Let's look at these numbers. Let's look at the numbers from 2 divided by 2 onwards. Because up to 2 divided by 2, that is plus 1, minus 1, plus 2, minus 2 and so on, up to plus 1 half and minus 1 half, they are unique, they are not repeated. Whereas, let us come to 2 divided by 2. If you reduce 2 divided by 2 to its lowest term, you will get 1, right? Because 2 by 2 is 1. And 1 is already here, listed here. So, we should not consider this. Similarly, minus 2 by 2, the lowest term is minus 1 and minus 1 is already here. So, we need not consider this. Similarly, 4 divided by 2 is 2. It's already listed. We should not consider this. Minus 4 divided by 2, minus 2 already here. We should not consider this. Same with 8 by 2 and minus 8 by 2 also. Now, we have to evaluate if any of this number is a root of our equation p of x equals 2x cubed minus 13x squared plus 7x minus 8. How do you do it? Let's take the case of 1 half. You plug in 1 half in place of x and calculate if p of x equals 0. If so, then 1 half is a root of the polynomial, correct? Similarly, we have to check for each and every number and see if they are root of this polynomial. And in case if none of them are root of the polynomial p of x, and according to rational root theorem, we can conclude that p of x has no rational roots and all the roots are either irrational or complex numbers. So let's do the calculations. We'll start with p of 1, right? So we have 2 multiplied by 1 to the power of 3 minus 13 1 square plus 7 multiplied by 1 minus 8. If you calculate this, let's see what we get. 2 minus 13, that is minus 11, plus 7 minus 4 minus 8 minus 12, so not equal 0. Therefore, 1 is not a root of the polynomial. Okay, next let's go to p of minus 1. Let's do this calculation. So you have minus 2, minus 13, minus 15, minus 7, minus 22, minus 8, definitely not equal 0. Therefore, minus 1 is not a root of this polynomial. Let's go to plus 2. Okay, let's do this calculation. 2 multiplied by 2 cube, this is 2 cube is 8, so this is 16, minus 13 multiplied by 4 is 52, plus 14 minus 8. Okay, so 16 minus 52 minus 36 plus 14 minus 22 minus 8, definitely not equal to 0. Therefore, 2 is not a root of this polynomial. Okay, then let's evaluate p of minus 2. Okay, so minus 2 cube is minus 8, so 2 into minus 8, minus 16, minus 2 square is 4, 13 multiplied by 4 is 52, minus 14, minus 8. This is definitely not equal to 0. All are minus 16, minus 52, minus 14, minus 8, not 0. So minus 2 is also not a root of this polynomial. Next, we'll check for 4. Let's look at this. 4 cube is 4 into 4, 16, 16 4, so 64. So 2 multiplied by 64, 128. So this is 128 minus 13, 4 square, 13 into 16. I think 13 into 16 is 208 plus 7 fours are 28 minus 8. This is definitely not equal 0 because 128 minus 208 minus 80 plus 28 minus 8 not 0. Therefore, 4 is also not the root. Similarly, we will check for minus 4 plus 8 minus 8 half and minus half. I'll write down, then we will discuss. Okay, so none of these numbers are root of the equation p of x equals 2x cubed minus 13x square plus 7x minus 8 because when you plug in these numbers, p of x is not equal to 0. Therefore, the polynomial p of x has no rational roots. All the roots are either irrational or complex number. Okay, so let me write that down. Therefore, okay, next we will see another example where we will get rational roots. Okay, and we are also going to show you a polynomial log division. Did I say some time back that the rational root theorem is not a method to calculate roots of the polynomial, but it only tells you whether the polynomial has rational roots or not, correct? But now I am going to turn the statement on its head and ask you to find out the roots of a polynomial using rational root theorem. So that's our next example. It reads like this. Using rational root theorem, calculate all the roots of the polynomial p of x equals 6x power 4 minus 11x to the power 3 minus 22x square plus x plus 6. But before we proceed, let's do some fundamentals. As a consequence of fundamental theorem of arithmetic, a polynomial p of x can be written in terms of its roots, correct? If Pn of x is a polynomial of degree n, it has n distinct roots and the same polynomial can be written in terms of its roots as follows. Okay, now what it says is if R1, R2, R3, etc. are n are roots of a polynomial Pn of x, the polynomial can be written Pn of x equals constant k multiplied by x minus R1, x minus R2, x minus R3 and so on up to x minus Rn. Now, this is a polynomial of degree 4 and let me call the roots of this polynomial as alpha, beta, gamma and delta. Therefore, P of x or polynomial of degree 4 can be written in this manner. Okay, so our polynomial P of x can be written as k multiplied by x minus alpha, x minus beta, x minus gamma and x minus delta, where alpha, beta, gamma and delta are the roots of this polynomial. Let me put a bracket here. Suppose we know the value of delta, that is, we know x minus delta, then the polynomial which is there, the bracket can be written as follows. Therefore, okay, I left this blank because this polynomial is a polynomial of degree 3. Why? You have the highest exponent as x multiplied by x multiplied by x. So highest term is x cube. Therefore, this will be a third degree polynomial. That is, polynomial of degree 3, correct? Okay, so that means our original polynomial is divisible by x minus delta. So that is what I want to tell you. Let me list out our roots here. Alpha, beta, gamma, and delta. Keep this in mind. Let's return to the original question. Okay? Okay, let us apply the rational root theorem here. We have this polynomial. A0 is 6 and An is also 6. Next, I want to calculate all possible rational roots, that is p divided by q, for this polynomial. Okay, let's do that. Okay, so p divided by q will be integer factors of 6 divided by integer factors of 6, because 6 is our a0 and 6 is also an. Okay, now what are the factors of 6? 1, 2, 3 and 6, correct? Okay, so from this I am going to calculate all possible rational roots. In any calculation of p divided by q, you will always find plus or minus 1. That is because any a0 or an in any polynomial is always divisible by 1. Therefore, plus or minus 1 is always thrown up as a possible rational root. In fact, in any rational root theorem calculation, it is always better to check your luck whether plus or minus 1 is a rational root or not. So that's what we are going to do here. I am going to apply p of 1 and p of minus 1 to check whether plus or minus 1 is a rational root. First, we will apply p1. So p1 would give me 6 into 1 power 4 minus 11 1 cube minus 22 1 square plus 1 plus 6. Okay, so this would be 6 minus 11, that is minus 5 minus 22 minus 27 plus 7, definitely not equal to 0. Therefore, p1, that is 1, is not a root of our polynomial. Let's try minus 1. We are going to try minus 1 now. So we have, okay, let's try. 6 multiplied by minus 1 power 4 is 1. So 6 minus 1 cube is minus 1. So minus 1 minus 11. So plus 11. Minus 1 square is 1. So minus 22. Minus 1 plus 6. So this is 6 plus 11, 17. 17 plus 6, 23. That is 23 in plus. And minus 22 minus 1, minus 23. So 23 minus 23 equals to 0. So we are in luck. Therefore, p of minus 1 is 0. Therefore, minus 1 is a root of this polynomial. That means x minus delta. Delta is minus 1. Therefore, x minus 1 divides, therefore x minus 1, that is x plus 1, divides p of x. So what we are going to do now is we are going to divide p of x by x plus 1 and get our polynomial of degree 3 here. So we are going to do a polynomial long division. I'm going to rub this and continue in the next screen. So in the earlier screen, we found that delta, which is equal to minus 1, is a root of our polynomial p of x. Therefore, we are going to divide our polynomial p of x by x minus 1, which is nothing but minus of minus is plus. So we are going to divide by x plus 1. So I'm going to write this as x plus 1. So I'm going to, okay, now we are going to do a polynomial long division. So let's start with the x power 4 term. So I have to supply 6x x to the power 3, right? So this will become 6x to the power 4 plus 6x to the power 3, right? So this gets cancelled. So plus becomes minus. So this will become minus 17x to the power 3. Then I bring the entire remaining terms down, right? Next, we have to look at the 17, or rather minus 17x cube. So I have to supply minus 17x square. So this will become 17 minus 17x to the power 3. So minus 17x to the power 3, then minus 17x square. These two get cancelled. You have plus here. So you have minus 5x square plus x plus 6. Okay. Next, I have minus 5x square here, x here. So I should supply minus 5x. So you get minus 5x square minus 5x. So that will give me, this get cancelled. So this will become plus, it's not 56, it's 5x. Okay, so you have 6x plus 6. Okay, then plus 6. So you will have 6x plus 6 here. Therefore, x plus 1 divides our polynomial, and the quotient is 6x cube minus 17x square minus 5x plus 6. So this is our cubic polynomial. This is our cubic polynomial. So alpha, beta and gamma should be root of this equation, correct? Next, I'm going to apply the rational root theorem to our cubic polynomial. Okay, so we have 6. Now I'm going to calculate the p by q for this polynomial, where a0 is 6, an is also 6. Therefore, all possible rational roots are. Okay, now I'm going to list out all possible rational roots. Then we will reduce the p by q's to their lowest term and knock off all repeat numbers. Okay. Okay, so these are all the possible rational roots of our cubic polynomial. So I'm going to reduce these numbers to their lowest term. Now you have 1 minus 1, 2 minus 2, 3 minus 3, 6 minus 6, half minus 1 half. Till this string, nothing is repeating. They're all unique numbers. Let us look at 2 divided by 2. 2 divided by 2, lowest term is 1. So 1 is already there. So we should not consider this. Same is the case with minus 2 divided by 2, because minus 1 is already there. 3 by 2 is unique. Minus 3 by 2 is also unique. Now 6 by 2. 6 by 2 is 3. It's already appearing. Same is the case with minus 6 by 2, because minus 3 is already there. Next, 1 by 3, minus 1 by 3. These two are unique, no problem. 2 by 3, unique, minus 2 by 3 also, no problem. It will continue. 3 by 3. 1 is already there, minus 3 by 3, minus 1. These two should not be considered. 6 by 3, 2 is there, minus 6 by 3, minus 2 is also there. So these two also goes. Now 1 by 6 is unique, minus 1 by 6 is unique. Then 2 divided by 6, 1 by 3 already there. So this should not be considered, this should not be considered. 3 by 6, 1 by 2 already there. So these two goes. 6 by 6 is 1, minus 6 by 6 is minus 1. So these two also goes. So these are all the possible rational roots, and I'm going to apply them one by one to see whether any of these are roots of our cubic equation. So these are all the possible rational roots, and I'm going to check whether each one of them is a root of this equation or not. Let's start with P of 1. I'm going to identify this cubic polynomial as P3 of x, just to differentiate it from our P of x, which is a 4th degree polynomial. P3 connotating 3rd degree polynomial. So P3 of 1 equals, so 6 minus 17 minus 5 plus 6. So 6 minus 17 minus 11 minus 5 minus 16 plus 6 definitely not equal to 0. Therefore, 1 is not a root. Let's check minus 1. So minus 6 minus 17 minus 23 plus 11 definitely not equal to 0. Therefore, minus 1 is also not a root. Let's check 2. Okay, then 6 multiplied by 2. Okay, so 6 multiplied by 8, so 48, minus 17 multiplied by 4, so that is 68, minus 10 plus 6. Okay, this is 48 minus 68 minus 20 minus 10 minus 30 plus 6 not equal to 0. Next, let's apply minus 2. So 2 is also not a root. Let's apply minus 2. Okay, so minus 2 cube is minus 8. So 6 multiplied by minus 8 minus 17. Okay, so minus 48 minus 64 plus 10 plus 6 definitely not equal to 0. Therefore, minus 2 is also not a root. Next, we shall try 3. Okay, so we have 162 plus 6, 168, so plus 168, minus 153 minus 15 minus 168. So this is 0. Therefore, 3 is a root of our cubic polynomial. So 3 is a root. Therefore, this polynomial is divisible by x minus 3, correct? So let us call gamma as 3. So our cubic polynomial 6x cubed minus 17x square minus 5x plus 6 is divisible by x minus gamma, which is x minus 3. So if I divide this by x minus 3, I'll get a quadratic. And quadratic is very easy to solve, correct? So let's do our next polynomial long division, that is divide this by x minus 3 in a fresh screen. Okay, let's start. So first term is 6x squared. So you have 6x to the power of 3 minus 18x squared. So this is minus, here it is plus, so this gets cancelled. Okay, so we have 6x to the power of 3 minus 18x squared. So the first term gets cancelled. You have plus here. So minus 17 plus 18. So it is just x squared. Bring this the remaining term down. Next, I have x here, x square here. So 6x square plus x. So x square minus 3x, correct? So x square, first term gets cancelled, you have a plus here. So minus 2x plus 6. So you have minus 2x here, x here. So you have minus 2 here. So minus 2x plus minus 3 multiplied by minus 2 plus 6. So this is our quadratic, 6x square plus x minus 2. I just have to factor this quadratic to get our alpha and beta, and we are done. So we are going to factorize this. So factorize 6x square plus x minus 2 equals 0. Okay, now we have a quadratic equation, 6x square plus x minus 2. There are different methods of calculating roots of this equation. One is the usual factorization method, where you take a multiplied by c and partition b in such a manner the partition adds up to a multiplied by c. That's one method. Second method is to use the completion of square method. And the completion of square method actually leads you to the usual, the famous quadratic formula, that is minus b plus or minus square root of b square minus 4ac. And there are different other methods. I'm going to use the completion of square method. And for the completion of square method, it makes sense to have the coefficient of the largest exponent as 1. So I'm going to divide this entire equation by 6. So that will give me 6x square, or rather x square plus x multiplied by 1 by 6 minus 2 by 6 equals. Okay, let me rewrite this a little bit differently. What I'm going to do is x square, I'll leave a gap here. Okay, then x multiplied by 1 by 6, leave another gap here. I'm going to take minus 2 by 6 to the RHS, so this will become plus 2 by 6, but that can be reduced to 1 by 3, right? Okay, now I have to convert this into the a plus b whole square, the binomial formula, by supplying the missing term. So let me multiply this by 2 and divide by 2. Okay, so to complete a plus b whole square, what is missing is 1 divided by 12 square is missing. So I'm going to add 1 divided by 12 whole square. But I have to compensate by adding the same term in the RHS. Now we just have to solve this. For x, you will have here two roots, that is alpha and beta. Let's do that. So this will be written as, this is x square, that is a square, plus 2ab plus b square, that is x plus 1 by 2 the whole square, another 1 by 12. So x plus 1 by 12 whole square. Let's simplify this. You have 1 by 12 square, that is 144. I can take 144 as a common denominator. Okay, so 144, I have 3 here. So 144 divided by 3 is 48. So 48 plus 1, 49. Okay, so we have x plus 1 by 12 the whole square equals 49 divided by 144. Take square root both sides. Okay, so whenever you take a square root, you have plus or minus sign. So this is plus or minus square root of 49 divided by 144. Both 49 and 144 are perfect squares. Therefore, this will give me plus or minus 7 divided by 12. So on the RHS, I have plus or minus 7 divided by 12. In LHS, I have x plus 12. So x would be so the two roots are 1/2 and minus 2 by 3. So alpha equals 1 divided by 2, beta equals minus 2 divided by 3. So we have half is the root and minus 2 by 3 is also a root. Now, do I need to check the other numbers? Not necessary, because fourth degree polynomial should have only 4 roots and they have all the 4 roots. So I don't need to check other numbers. So these are all not the roots of our polynomial. So the 4 roots of our polynomial, 6x power 4 minus 11x cube minus 22x square plus x plus 6 are 1/2 minus 2 by 3, 3 and minus 1. So I have used the rational root theorem to calculate root of our fourth degree polynomial. But earlier I said that rational root theorem only gives you the method to find whether the polynomial has rational roots or not. But we have turned the statement in the head to get our roots. I am going to use the rational root theorem in my next question in trigonometry. Thanks for watching.